welcome back to our channel. We're thrilled to continue exploring the fascinating world of differential equations with you. In our previous videos, we introduced some foundational mathematical concepts and essential tools you'll need for our method. We assumed a basic understanding of mathematics to get started. Each video in this series builds on the knowledge from the previous ones. So, we highly recommend watching them in order and practicing along the way, because practice is the key to mastering mathematics. Today, we're diving into the fascinating world of differential equations. So, what exactly is a differential equation? Simply put, it's an equation that connects an unknown function with how that function changes. It involves the function itself and its derivatives, which show how the function's values change over time or space. Imagine a car driving along a road. We can track its position over time using a graph. At any given point on the graph, drawing a line that touches the curve at that point, called a tangent line, shows how fast the car is moving at that exact moment. The steeper the slope of this tangent line, the faster the car is going. A differential equation can describe how a car's position, speed, and acceleration are related. For example, if we know how a car's acceleration changes with its speed, we can use a differential equation to represent this relationship. By solving this differential equation, we can predict the car's position and speed at any point in time, helping us understand how the car moves over time. Imagine a basketball in midair. We can explain how the ball moves using differential equations, which take into account forces like gravity pulling the ball down, and air resistance slowing it down as it travels through the air. By solving the differential equation related to the basketball's movement, we can predict how its speed and position will change over time. By solving differential equations, we can assist players and coaches in refining their shooting techniques. This mathematical approach helps improve accuracy by identifying the ideal angles and velocities required for successful shots. Scientists use differential equations to model various phenomena, such as the spread of diseases. This analysis helps them predict and prepare to control the disease's spread effectively. Engineers rely on differential equations to analyze structural stress in buildings. This process enables them to predict, for example, how beams will bend under different loads, ensuring the safety and stability of structures. If you're enjoying this video so far, don't forget to like it, share it with others, and subscribe to the channel for more videos like this. If you have any questions or thoughts, drop them in the comments below. We'd love to hear from you. We have explored how differential equations and their solutions play a crucial role in modeling and predicting real-world phenomena. But what does it mean, mathematically, for a function to be a solution to a differential equation? Let's dive deeper to understand this concept. A solution to a differential equation is a function that, when substituted into the equation, satisfies the relationship defined by the equation. We've already discussed differential equations, why they are important, and what their solutions represent. Now, let's take a closer look at two essential types of solutions: the general solution and the particular solution. A general solution shows all the possible ways a system can behave based on different starting conditions. For example, imagine shooting a basketball. The general solution gives you all the possible paths the ball could take, depending on factors like how high or fast you throw it. Each path comes from different starting points, and the general solution shows all those possibilities. A particular solution is a bit different. It gives you one specific answer based on the conditions you know. For example, if you know the exact height, angle, and speed when you shoot a basketball, the particular solution will tell you exactly where the ball will land. It's like getting one clear path that depends entirely on those starting conditions. There are two main types of problems that lead to specific solutions. Initial value problems, IVPs. These involve knowing the starting point or initial condition of the problem. Boundary value problems, BVPs. These involve knowing the conditions at two or more different points. In an initial value problem, we are given a starting point, also known as the initial condition. For instance, think about shooting a basketball. The height, angle, and speed at which you shoot the ball represent the initial condition. The differential equation then helps predict the path the ball will take through the air, showing how its position changes over time. In a boundary value problem, you're given the conditions at two specific points. For example, think about trying to shoot a basketball so that it starts from a certain height, where you are, and lands in the hoop. The conditions at both the starting point and the hoop, the boundary, are crucial in this situation. In this case, you adjust your shot by changing the angle and speed to make sure it meets both conditions, where you start and where the hoop is. Boundary value problems and initial value problems are two types of differential equations commonly encountered in mathematics. An initial value problem involves specifying the value of the solution at a single point, which typically makes it easier to solve. In contrast, a boundary value problem requires the solution to satisfy conditions at multiple points. This added complexity often makes boundary value problems more challenging to solve. Both types of problems play a crucial role in many scientific and engineering applications, and understanding their differences is key to mastering differential equations. In addition to general and particular solutions, it's important to recognize that solutions to differential equations can also be classified as explicit or implicit. Explicit solutions. These solutions express the dependent variable directly in terms of the independent variable. For example, you might see an equation like y equals x squared, where y is clearly defined by x. Implicit solutions. In this case, the solution involves both variables, but neither is solved explicitly for the other. For example, the equation y squared plus x squared equals 1 shows a relationship between x and y, but neither variable is isolated. So, while we often talk about general and particular solutions, don't forget that explicit and implicit solutions offer another way to categorize the solution to a differential equation. When we solve differential equations, One of the solutions we can find is called a closed-form solution or analytical solution. These solutions give us exact formulas for the variable we're solving for, using a finite number of basic mathematical operations like addition, subtraction, multiplication, division, and exponentiation. These solutions are written in terms of well-known functions and constants, giving us clear, precise expressions for the variable we are interested in. For example, let's look at the differential equation. dy over dx equals y. The closed-form solution to this equation is y equals c times e raised to the power of x. Here, c is an arbitrary constant. Not all differential equations have exact solutions. In these cases, we turn to numerical methods to find approximate solutions. Numerical methods rely on software and programming languages, like MATLAB or Maple, to solve differential equations that can't be solved exactly. Some commonly used methods include Galerkin, finite difference, and Runge-Kutta. However, in this series of videos, we will introduce a more efficient, robust, and better method that improves upon these existing techniques. Stay tuned to learn more. Differential equations can be either linear or nonlinear. While linear equations have well-established methods for finding solutions, nonlinear equations are much more challenging. In fact, many traditional methods struggle to solve nonlinear problems, especially boundary value problems. However, our method stands out because it works exceptionally well for both linear and nonlinear equations, providing reliable and accurate solutions where other methods often fail. A linear differential equation is one where the unknown function and its derivatives appear only to the first power. This means that they cannot be raised to any powers other than 1, and they cannot be multiplied together. Also, the unknown function and its derivatives are not combined with nonlinear functions, such as exponentials, logarithms, or trigonometric functions. For example, consider this equation. Y double prime equals y prime plus 3y plus x squared. This is a linear differential equation because the function and its derivatives appear only in the first power, and there are no nonlinear functions involved. If a function is not linear, we call it a nonlinear differential equation. For instance, the following equations are examples of nonlinear differential equations. Y double prime equals y squared plus y times y prime. Y double prime equals negative sine of y. These equations include terms that involve nonlinear functions, such as sine, or terms where the unknown function and its derivatives are multiplied together. Recognizing whether a differential equation is linear or nonlinear is crucial because it determines the methods used to solve it. While existing methods often struggle with nonlinear equations, our innovative approach resolves them with precision and efficiency. This method is particularly effective for boundary value problems, or BVPs, as we will demonstrate in the upcoming videos. Thank you for watching our video. In the next video, we will begin solving initial value problems in differential equations. See you soon.